Okay. So what I want to do today is kind of take care of some loose ends. I want to start getting to the idea of the Carnot engine. There's at some point I'm going to prove that that's the most efficient heat engine you can have. The proof for that is, oh, good grief. It's not hard, but it's one of those that's really kind of a subtle argument. So I think I might get everything up to that and then just finish that proof on Monday. That would not be on the exam. The exam will go basically, the exam will end with PV diagrams calculating efficiencies for engines, but nothing with the Carnot cycle or anything like that we have. So there's a couple of little last minute things I want to do. We talked about the two other statements of the first, second law. I want to convince you that if you violate one, you violate the other. And so there's a couple other first law things I have to do. And I think there's a derivation I did for the second law that in my head we did it. Looking over stuff here, kind of doing some stuff yesterday, I think I did not do it. I think actually we have to do that proof. So we'll go back and do the proof that in my head we did it perfectly and everyone agreed and nodded. And I think we did not do this. Okay. So a couple things here. So we had the Kelvin Planck statement. The second law. And then we had the Clausius statement. Oh. On the second law. And then we're going to have another one down here too, and then I'll try to convince you that basically if you violate one, you violate them all. So they're all equivalent statements. Okay, what did the Kelvin Planck statement say? There are no
perfect heat engines.
Yeah, so there are no perfect heat engines. Okay, what does it mean to be a perfect heat engine? All the energy you supply
Goes into work.
Yeah, so this basically states that all the energy you supply goes into work. Again, if you draw the little cartoon picture of this, here's our high temperature reservoir, some TH. We extract some amount of heat that we're going to dump into our engine. So this engine is going to do some work. This is our C at some temperature TC. That's what it means. Basically, there's no waste heat. Basically, i.e., all the supplied heat goes into work. Okay, then what did we say about the Clausius statement?
No perfect refrigerators.
Yeah, there are no perfect refrigerators. Okay, what does that mean?
No work required to move heat from low temperature to high temperature.
Yeah, so no W is required to move heat. This at TC to QH. Okay, so again, if you draw your little cartoon picture of this, here's your TH, TC. Basically, you're going like that. There's no work involved. So the QC here and the QH here, these are equal. This says that QH is QC. The perfect heat engine says that QH. So this statement states what? Basically, that heat cannot spontaneously flow from cold to hot. So in other words, heat cannot spontaneously flow from cold to hot. Okay, I want to say something about this, and I want to show you that this file, if you had this violates zone 1. Then I want to show you that basically, if you have this one here, you violate this one. If you have this one here, you violate this one. I want to show you how this works. So they're all completely equivalent. So we need a couple of things here. So recall that our original sheet of the second law stated that if you look at the change in entropy for some system here, that this is greater than or equal to 0. Okay. So basically, if you have a spontaneous process occurs, that if you look at the whole thing here, the entropy of the whole system always is greater than 0. Does that make sense? Okay, now I don't think we did the proof for this. I think we did the examples with the boxes and the partition functions, but I don't think I did a general proof.
I don't think so.
So this is a general proof. Okay, proof. Because we need this and then some other, we want to put this all together. So let's say I have two systems here. This is system 1, and this is system 2. And these are initially isolated. They're initially isolated microcanonical systems. So consider 2 initially. Uh-oh, is that going off the board?
I think it might be.
We're so fine for a little bit. There are 2 initially separated microcanonical systems. This is going to have some energy. I'll call this E1 naught. This has some energy E2 naught. But this is an energy some E1 naught. This would have some degeneracy G1 of E1 naught. This would have some degeneracy here too of E2, G2 at E2 naught. Does that make sense? That's just your initial situation.
This does seem familiar.
Okay, did we?
Let me.
It does start off very similar to another. Because we're going to go to this, we're going to get this guy here. Then we're gonna go. So this is going to be something. So
Sort of separate.
yeah, this is
than when
this
the-
is equal.
Yeah,
I don't think we did that.
no.
But it's going to, it will be very similar because it's not that dissimilar.
Right.
Actually, it was when I printed out the review sheet. I was looking over what was in the review sheet. And I went, uh-oh, I don't think we did that. Yeah, the second law is very passe. That is all 2019 stuff. We don't need it now. That is all pre-COVID. That's pre-COVID physics. This is all post-COVID physics. Or during COVID physics.
Yeah.
Okay. So let's put these two systems together. This is system 1, this is system 2. And so what can happen here? Well, energy can go back and forth between the two. So let's say this has some energy E1, and this is some energy E2. So this system now has some degeneracy G1, E1. And this has some degeneracy here, G2, E2. So what would be the G of the entire system? Then what do we also know that the E1 plus E2 equals E total. So what did we say the degeneracy of the whole combined system would have to be?
There's G1 times G2.
Yeah, it'd have to be the G1 at E1 times G2 times E2. Now it's just not that. Because what do we know about the E1 and the E2? That can actually vary. So if you want the total degeneracy, what would you have to do? This would be if you had a fixed E1 and a fixed E2. We don't have a fixed E1 or fixed E2, so what do we have to do?
We need to do the partial with respect to.
That's when we do the maximum one. So I tied this into the other proof. So following the total, I'd have to sum over all possible values of E1.
Okay,
Why don't I have to sum over all possible values of E2?
because it's related to the E1 by a constant.
Yeah, if you vary this here, then you can see you're getting that one at the same time. Now, okay, just to tie this into what you had before. Now we said, remember how we tied this in equilibrium? When we tied this in equilibrium, we said, what? When this system reaches equilibrium, we said there's going to be some maximum term here. Right? And so we basically said this whole thing here is approximately equal to that maximum term. And then we then differentiate, if that was truly the maximum value, then we could differentiate that and that give us the equilibrium condition. This is saying something else. Okay, this is just a general thing. Okay. Now, I can write this in kind of a stupid way. I can separate out the initial energy here because basically it's included in that sum. So I can actually write this as G1, E1 naught, G2, E2 naught, plus the sum here where this E1 is not equal to E1 naught. So basically I'm splitting the sum up into two pieces. All the pieces of E1 that are not E1 naught, so the E1 naught value. Does that make sense?
Yes.
Okay, to be honest, we're almost done with the proof now. So this is actually the subtlest part here. So this is positive, this is positive, this is a positive term. These are all positive, so everything is positive over here. So I'm taking a positive quantity plus a positive quantity, and that equals a G system. Well, that means that this whole system here, if you look at the whole thing, has to be greater than just this piece here. So I can say that G of the system here is greater than, okay, or equal to just this piece right here.
And that would be G system naught.
Correct. This right here, the G system is the whole thing here.
Yeah.
Okay. It's saying that this has to be greater than or equal to the base of the initial condition over there. This would be if that system just had some energy E1 0 plus E2 0, and you get E2 0. Okay, let's take the log of everything. To be honest, we're done now.
Yeah.
We take the log. That's the same thing as log of G1, 0, plus log of G2, 0, multiplied by KB. Multiplied by KB, what does this? This gives us basically the final momentum here, that system. Has to be greater than or equal to basically this S1 initial plus S2 initial. If you take the initial entropy of system 1 plus the initial entropy of system 2, this would be nothing but the initial. So I can take this over here. Here. So this is my delta S. This will be greater than or equal to 0. That make sense?
Yeah.
So this is the second law. Now, let's tie this into basically the other statement. So I want to show one other thing here. This version of the second law states implies that heat must flow from the high temperature to the low temperature. So what I want to convince you of is that if it doesn't go like this, then you violate this law here. And then we can go through and I want to show you how all these things are connected. Make sense? Yeah, so this is okay. So let's consider two large systems. Okay, let's consider two systems at temperatures T1 and T2 that exchange a small amount of energy, delta Q. Delta Q is small enough that neither system, that neither temperature, that the temperature of either system changes. So here's system 1, some temperature T1. Here's system 2, temperature T2, and the temperature is going to go like this. That's going to be the energy exchange. Okay. And let's assume that T2 is going to be greater than, so this is going to be hot temperature than T1. Let's see what happens here. Let's ask what is delta S for the system. So let's delta S here in the system. The delta S of the first system. What's the delta S of the second system? Again, we're saying that this is so small, or that these systems are big enough that this little temperature change, this little heat added or removed, doesn't change the T. Okay. So what is this guy here? This guy here is going to be delta Q over T1. Now, is that going to be a positive Q, a positive delta Q, or a negative delta Q in this configuration like this? What is that? This is the heat being changed. So is this going to be positive or negative for this one over here?
Negative.
It's going to be negative. Okay. Plus, then what does that have to be over here then?
Positive delta Q.
Delta Q. So I can rewrite this as delta Q is 1 over T2 minus 1 over T1. Now, we have this condition here. At T2 is greater than T1. So which term there is larger?
The 1 over T1.
Yeah, so T2 here is greater than T1. Okay, so this term is larger. So this whole thing here is less than 0. So you can see here, if you assume that making the assumption that this is hot and that this is cold. So if you assume that energy goes from the cold system to the hot system, you basically get this being less than 0, and that violates the second law. Okay, does that make sense? Now, if I went the other way, if I went like this, let's just convince you that that's fine. So if, let's look at this case. So if E flows from 2 to 1, so in other words, it's going from hot to cold. Let's see that this doesn't. This is fine. Now what does delta S1 equal?
Delta Q over T1.
Yeah. If you look at this case, this is delta Q over T1. Plus, what is my delta S2?
Minus delta Q over T2.
Minus delta Q. This guy. This is positive. So this is actually greater than 0. So that's fine. That makes sense? So now let's apply everything. So first, okay, so now let's go back and look at the Kelvin Planck and all those other things. In the case that ever happens, okay, so in grad school, when I took statistical mechanics, there's a very, very good professor who I liked. I got to the point where I didn't care what he taught, I just always took his courses. And he asked this one question, I'm still kind of pissed off at it. So the question is, you have a room here. There's a room. You have a window here. I guess this was he was at I don't know if this is a question that came from MIT or it came from Cambridge. He was English and he was from Cambridge. Absolutely brilliant guy. Here's the window. You have sunlight coming in here. So here's sunlight. He claimed that this was a qualifying exam question. I think he said MIT, which is if this wasn't, it's just moronic. And here's some water. So sunlight's going to come in here. Okay, so which side of the water is going to be warmer? The side closer to the sunlight coming in here.
Yeah.
So this side's going to be a little bit warmer than this side here. Eventually reach equilibrium, but when the sunlight comes in here, this is going to become warmer and then this side's going to become colder. Okay, so this is going to become hot and this is going to be cold relative to one another. Okay, so the question is, you come into the room. And here's the water, and you measure this, and this is cold, and this is hot, and the sunlight's still coming in here. How did that happen? I'll give you a hint. The answer is asinine. Evidently, they claimed that this was asinine. I actually asked it as a homework, and this created a big brouhaha amongst my friends. And somebody who actually claimed to be from he would claim he was from MIT as an undergraduate, was familiar with it. He went, this is the answer. Went, that's obviously not the answer. He went, yes, it is. And he was right. Okay.
The engineer in me says someone turned the glass.
That's the answer. That's the answer. So the answer is that somebody went in there before him and turned the glass room. So are you kidding? You know, that's
wow.
Why the hell would you ever ask that? I mean, that is just a jackass question. I mean, so like, no. Okay, so if I knew this is that is the answer. Still ticks me off to no end. Okay, so
I can imagine. I can see why.
I mean,
That's
we racked our brains over that. And we couldn't come up with anything that made any sense because it doesn't make any sense.
oh.
Okay, so now let's put all these pieces together. So, how are all of these statements of the second law related? Okay, none of this stuff here is actually going to be in the on the exam, the second law stuff. I'll have the PV diagram stuff, but none of these statements here, the second law and the Carnot engine and stuff like that will be on there. Okay. So what I want to convince you is that if you violate, here's the answer. One of these statements. Of the second law. You violate the other statements of the second law. Okay. So these are we're going to have basically similar proofs. So let's see how we can do it. So let's assume. So here's a proof. Let's assume that the Kelvin-Planck statement, the second law, is false, and that perfect heat engines exist. Okay. So in other words, you can have one. So what we're going to do is use the perfect heat engine to run any refrigerator. So get your perfect heat engine, take any refrigerator you want and connect it to it. What we're going to find out is that then you're going to get a perfect refrigerator. Oh. So let's do that.
Okay. I wanted to see how the perfect refrigerator, I understand how that violates the first statement.
We're going to do them both. Okay. So okay, so we go to Lowe's and they're having a sale on perfect heat engines, and there's our perfect heat engine. We're going to connect this. So here's our perfect heat engine. This is a TH. This is a TC. This is some QH here. This is W. And this is our perfect heat engine. Turns out they're having sales on generic refrigerators. So here's our generic refrigerator. So this is going to pull up some QC here like this. I'll put primes in these guys here, and then it's going to dump in some heat like this. So here, what do we have on this side? We have QH equals W. This is this guy. And this guy, what do we have on this side? We have W plus this QC prime equals this QH prime here. I'll bend up a little absolute value here because that's technically negative because it's being dumped out here. Okay. Well, what do we have here? That's the saddest. Yeah, I love this one. Okay. I can take this right here and put it up into here. So this goes in QH plus QC prime. It's QH prime. So this tells me that QC prime was QH prime. This right here. Okay. That right there is going to be positive. Okay. So what is this? Well, you can see if you look at these two pictures together, this is equivalent. Let's kind of show on the board. I am still on the board, or the camera. We can see what happens if you basically then look at these two here and kind of add them together. What happens? You really get something that looks like this. This is what this statement means. This is your QH prime minus QH. Here's our refrigerator. Here's our, our motor that does really nothing effectively. Here's your QC. GH, and that's what it does. Straight like that. If you want, you can just take this guy out. You didn't even really need it because it's not there if you add these two together. This violates. This is a perfect refrigerator. That makes sense? So this violates. We assumed that we had a perfect heat engine. That ended up forming a perfect refrigerator, and this violates the Clausius statement. For the second law. But we're also going to have heat going from cold to hot, so this also violates delta S as being greater than or equal to 0. Okay, that makes sense? Okay, how are we going to do the other one? First of all, what happens if you, let's say you had the, okay, let's do that one. So now, how are we going to do the next one? We're going to assume we have a
perfect refrigerator.
Yeah, let's assume we have a perfect refrigerator. And we're going to connect it basically to our just a generic thingy to generic heat engine. Okay, so let's assume that Clausius statement of the second law is false. So that perfect refrigerators exist. Connect perfect refrigerator okay, to a generic heat engine. So let's see what that picture looks like. So here's our perfect, here's our generic engine like this. You see, I'm going to take that. That's going to be negative, so it's like this. So that means this. Okay. What are we going to do? So all this heat is being dumped in here. So what are we going to do? Well, we're going to put our perfect refrigerator here. So here's our perfect refrigerator. So basically what this exhaust is having here, we put our perfect refrigerator. So this exhaust here, this would be QC here. Then be this QH
You want to use the primes?
Yeah, I use a prime like this. Okay, so we're gonna have that. Okay. So what's gonna happen here? You can see, well, if you add these two together, what's gonna happen here? If you add these two together here, this QC prime, you're taking all this heat and putting it in here, so this QC is really gonna be this guy here, like that. So if that's like this, then what we're gonna have, if we add these two pictures together, what we're left with is this guy here, and this is W. Okay. They're gonna cancel here because the heat going out, the heat going up, or like that. This guy right here, this is gonna be our QH, then minus this guy here, minus QH. From here, and so what this is here, this is a perfect okay, that makes sense.
Yep.
So if you assume you have a perfect refrigerator, then you basically violate, which is violating the second law of Clausius, then you violate the Kelvin-Planck statement. Now if you have a perfect refrigerator though, this automatically violates what?
Automatically violates delta S squared.
Yeah, so this one here, this automatically violates. Delta S and greater than or equal to 0. Okay, so a violation of one is a violation of all of them. Now, do you know where one of the really, I think I mentioned this before, maybe briefly. Do you know where one of the big areas of thermodynamics is today? It's not one bit obvious.
What is it?
Applying it to black holes. Okay, Stephen Hawking is famous, and they're just not him. Is that during the 70s, basically a lot of the ideas of thermodynamics were applied to black holes. It turns out that you can have like here's a situation. Let's say here's a black hole. Okay. And let's say you have something with some entropy here. So here's, who knows what it is. This is just something with some entropy. So what's going to happen is that if you have this thing with entropy in your black hole, this is just going to spontaneously go in here. It'll be attracted, it'll go in there. So what happened to the entropy? You could say, well, there's no entropy here. Well, if you say that the black hole has no entropy, then you've just violated the standard version of the second law. This had entropy, a spontaneous process occurred, and now delta S is now less than 0. You had something with entropy, now you have nothing with entropy. This would be delta S is less than 0. That violates the standard second law. You could say, well, maybe black holes actually satisfy them though. So obey the second law. And so what has to happen here is that if this goes in here, the black hole has to have entropy and has to be greater than the original thing. So you can still say that, well, you can say, well, maybe black holes still obey the second law like this. But once you do this, what happens is then it turns out a black hole that has a temperature. So it turns out black holes have a temperature and they also have an entropy. Well, what Stephen Hawking was able to do, he applied quantum gravity. Well, he didn't apply quantum gravity. He applied quantum mechanics to the black hole, which turns out to be actually quite hard to do. It is actually able to show that if this black hole has a temperature, it actually radiates like a black body radiator.
Mm-hmm.
And so that's something called Hawking radiation. And so that's actually why he's well known. But one of the big areas, modern areas of thermodynamics is actually the thermodynamics of a black hole, which is, you wouldn't think a heat engine is going to apply it all to a black hole. Turns out it does. Okay. That's quite cool. Okay. So let's do one other proof that we're okay. So let's start something and then we'll finish it on one day. But we'll get one more proof that I will hold you responsible for. I said we're going to do it. So let's ask the following. You can say, Is there a heat engine with a maximum so is it possible to have a heat engine that's as efficient as you can ever have? The answer is yes. Okay. This engine is called the Carnot engine. Okay. No, spelling is not my strong point, but I am actually spelling Carnot correctly.
Yeah.
He's French, that's why the T is not pronounced because it doesn't end with the E. So it's Carnot. Carnot engine. So I want to give it to you, then I want to do one proof, and then on Monday I'll prove that this is the most efficient heat engine you can have operating between two temperature extremes. Okay, so Carnot cycle is, I'm just going to state this and I'm going to prove it. Oh, I want to do one more proof. Okay, you probably have this in your course. Let's know what you remember of it. I'd be surprised if they didn't do this. So let's look at, okay, always look at the isotherms first. So these are isotherms. Okay. So what do we do with the Carnot engine?
It was an isothermal expansion.
Okay, good. So we're going to start here. I'll call this A. So we're going to do an isothermal expansion here, just from point B. This will be at some temperature TH.
Then you have
Adiabatic expansion to some point here, C. So this is adiabatic.
Then you have isothermal compression.
Yep. So this is going to be this isotherm here is at some temperature TC. So you're going to have an isothermal compression here.
Adiabatic.
Yep. Compression. Okay, at TC. And then you basically, this would be point D. And then you're going to have then an adiabatic compression. But that's not very compression, is it?
Okay.
There we go. This is adiabatic compression. Back to A. That is a Carnot engine here. And it turns out that's the most efficient heat engine you can have operating between two temperature extremes like this, TH and TC. You can't get more efficient than that. And to go and prove this, we need to, we're going to prove this. We're going to start the proof today. Actually, we're not. We're going to start it on Monday. But we need one result that I said we would prove on. I think I lied to you twice. I think I told you we're going to prove it on Tuesday. Then we didn't. I told you on Wednesday, but we didn't. So now we're going to do it. Okay.
Is this
So
the adiabatic?
yeah, we're going to prove it.
Okay.
So before we can prove this, so before you can show that the Carnot engine is the most efficient. Between two temperature extremes. We need to prove that PV to the gamma equals a constant for an adiabatic process. And that's still legible here. Okay. Proof. The proof is actually just being careful. So, what's the definition of an adiabatic process?
Delta Q equals 0.
Yeah. So this is delta Q 0. Okay, I'm going to write it as dq. dq equals 0. So what does the first law become? So since dq equals 0, I can say that the first law here
U equals minus dw.
Yep. And how can you write dw?
Equals minus pdv.
PdV. And how can we always write that du? And CV
and cv
dt. So I can solve this for dt. So this tells me dt is minus PdV over mcv. Does that make sense? Well, this result is only true for an ideal gas. So what do you know about an ideal gas?
Non-interacting
Sure.
and no volume
Sure.
for
P.
PD equals nRT.
P equals nRT. Okay, let's take the differential of this. So dP, and you got it finished up. You're gonna take the differential of this. dP V plus
dPV equals
dPV. I'm gonna take the differential of this. Product rule.
plus PDV
PdV equals NR
nRDT.
dt. So divide everything through by the NR. This is dt. And I'm going to equate that dt to the one over here. That makes sense?
Yep.
Okay, so I'm going to get rid of those super little ends. I take the P to the other side. The PdV to the other side. Let me see. So this gives me P, gives me this from here. All right, this is VdP over R. I just rewrote this one, plus this guy over R. And this side equals positive. PdV plus CV equals 0. Okay, let's get a common denominator here. So I'll multiply this one by CV, and then, oh, I shall pull this out. I'll pull out the dB first. We get a common denominator here by multiplying top and bottom by CV, and then this one here by R. So this gives me CV plus R over RCV. One nice thing happens. The R is go out. What do I know about CP plus R?
CP.
That's CP. So this gives me VdP plus CP over CV, PdV equals 0. This right here is the definition of gamma. Now divide both sides by VP. divide both sides by dp, this gives me dp over p plus gamma dv over b equals 0. Okay, now what? Almost there. Integrate both sides. Hold on a second. I'll solve. Tell me when you're done.
I'm good.
Okay. Okay, the integral dp over p is
L1B.
p plus gamma dv over v is
Gamma L1B.
gamma ln v, and then equals a constant. Okay, so what can I do with the gamma here in front?
Where is it? Move it inside the line.
So this is ln of v to the gamma, ln of p. Now what? We're done.
Combine the LNs.
Now this gives me the ln of p v to the gamma equals a constant. And what do I do to both sides?
E to the power both sides.
Exponentiate both sides. This is e to the constant. The e to the constant is a
Constant.
constant. So we get PV to the gamma. Pretty slick. Make sense?
Yeah.
Okay. So on Monday, we will not then show the that the Carnot engine is the most efficient engine, and I really hate that proof. It's one of those where it's a little on the subtle side. You're not going to do anything really sophisticated, but it's one of those we're going to basically assume that we have something more efficient than the Carnot engine. Then we have to be careful how we set things up, and it's just it'll all come out all fine, but we'll see that we can't get anything more efficient than the Carnot engine.
Okay.
And then we'll look at a couple other things about the Carnot engine, and then say something about a car, because I think I should say something about a car. I think we're done with those engines. I really don't like engines, but yeah, it's one of those things you have to cover. Okay. Take care. Have a great weekend.